So let's talk about Superspace Theory, my new book out on Amazon. So a quick disclaimer, other than my own line drawings, some of the graphics I will be using are not my own, and I just use briefly under fair use policy just to demonstrate some of the ideas in this book, along with my own line drawings which are from the book itself. So Superspace Theory is a book that puts forth a new vision of physics and geometry and cosmology. And it is centered around what I call the principle of the equivalency of size and distance at fundamentally smaller levels of physics. So we will be focused on this principle, but there is a lot around the principle and sort of conclusions that can be drawn once you accept this principle that are also interesting and important. So Superspace Theory, I will go ahead and pull up the Amazon page, is out on Amazon now, just published. And so I have, besides the book, I'm working on an article that will be posted along with this video in order to spread this idea. So I will go over these points and develop them a little bit and then backtrack when needed. So the first point is that we have to see the universe, not just our universe, so this will be clearer as we move forward, but the universe as a what I call a block universe, and I don't use this quite as other individuals have used it with other ideas, but for me the block universe is simply seeing the universe as a long block of space which includes our own three-dimensional universe as well as other layers or fields within it. So as you can see, the second point we have here is that the block universe is made of fields. And so what I'm going to do is go to my graphics here and pull this up. So I have right here the block universe. I have some funny little pictures just to make it entertaining. So I will not go into all the details of what we have down here, absolute motion, and then up here, stillness or void. But what I'm basically saying is that there is a level of essential energy under all these layers of space, and that it progresses toward basically stillness or entropy. So you could just, although I use various terms, you could just say progressing from energy toward entropy. So that would be the block universe, and it would be made of fields. So there would be layers of space moving from the energetic to the entropic. Again, this will make more sense as we get into the central principle of the equivalency of size and distance and how these different fields are existing alongside each other as basically universes or planes of space, fields of space that are equal to our own universe. So one thing we will be doing is looking at space from a lower dimensional analogy. So although we live in a three-dimensional space, and then when people talk about space-time, they say four-dimensional space-time, or rather 3 dimensions plus time makes, space-time four-dimensional. But we will be looking at it from a lower dimensional analogy in which each three-dimensional spatial field, we'll examine it from a 2D perspective just to make it easier. And this was done in the Buck Flatland, which was more of a satire, but they looked at space as sheets, 2D sheets, rather than trying to explain all this as three-dimensional space. So as we talk about superspace theory, we're going to look at our universe. So this would be our universe, but you could just say it's a universal field or a spatial field as a two-dimensional sheet. And there are deeper dimensions lying alongside or under the two-dimensional field, or the field, which is, actually three-dimensional, but the field of our universe. So you have, up here you could say is our universe, and then you'd have another dimension, and you'd have another dimension. And so as I, right here, you have two directions, which are the linear and the nonlinear. So when we move within this sheet of space, that would be the linear direction, linear space. And as we go deeper into fields that lie under our universe, our field of space, that would be the nonlinear. And all of this makes more sense when you understand the equivalency of size and distance at fundamentally different levels of physics. And so we are getting to that now. So the equivalency of size and distance at fundamentally different levels of physics. At fundamentally smaller levels of physics, what we perceive as size is actually distance. When we look into the realms of the very small, we are looking in a fundamentally different direction, leading into another dimension of the universe, a fourth spatial dimension. So this is core, and this is hard to wrap our minds around. But what it's saying is that even though you can have larger and smaller within our universe, within space, as you go inward to the point of subatomic realms, so let's look at this top picture here. This is the flat or linear view. So you're looking at it just as a flat sheet, and we look at it as going inward, smaller and smaller and smaller and smaller and smaller. That's how it appears to us. And even though we live in 3 dimensions, we're looking at it in this same flat way. So superspace theory, this main principle, is that down here, we can go inward or outward in the linear directions. But once we get into the subatomic realm, we're actually curving. And actually, I'm going to open this with GIMP, which is my image manipulator, in order to be able to show this a little better. So the idea is that, take a brush, that we can be going in, so say, let's make some circles here. And it's like up here, so we're going in, smaller and smaller, right? Well, toward that. Going in, smaller and smaller, right? But at some point, and we'll make this a little thicker, at some point as we're going in, when we reach the subatomic realms, we're curving in a fundamentally different direction. So that's what's hard to imagine, but this is actually what is in the mathematics. What is in the mathematics is that when we curve inward with gravity far enough, it actually curves into infinity. So this is what two things. One is the math that is behind black holes and the singularity that caused the Big Bang. So the math is saying that so we're going in, and here's, you could look at this as, we could say this was a black hole, right? And so it is a hole and you're curving inward. Well, this inward curve is infinite. I can't really do writing with the mouse, but there we go. Is infinite. And so this is what the math says, except we're only allowing it for things like a black hole. But this is curving into infinity, right? And so when we talk about a black hole, we say it curves to a singularity, which is a point of infinite density. But actually, when you're speaking of the infinite density and infinitely small aren't concepts that actually make sense, because we're speaking of infinity. And what the math is actually saying is that this direction continues infinitely. This direction of the very small, once you move into the realms, fundamentally small, so-called smaller realms, this direction is infinite. It goes infinitely. So for it to be an infinite line going out of the picture and beyond, that is no longer smaller. That is a fundamentally different direction of spatial reality. That's a fourth direction showing the fourth dimension, which is lying alongside our own familiar space. So if we go back to this and go down here, so these two crosses in the lower dimensional analogy would actually be 3D space, right? So when we talk about 3D space, we talk about 3 degrees of freedom. So we do the, three, so there'd be, 3 degrees of freedom, and there'd be a third, going like this. So 3 degrees of freedom. So if we can go inward infinitely, that is a fourth direction, a fourth degree of freedom. So that is a fundamentally different spatial dimension lying alongside our own 3D space, although this is very difficult for us to imagine. But in fact, this is the same fields of space which we talk about when we talk about something like quantum field theory, which I'll get into. But what holds fundamentally smaller particles. So let's just go to the idea of quantum field theory, because it does relate really well. And I don't know if I have it in here. I talk about a fourth dimension or spatial direction. The fourth dimension is the direction of very small, or the direction inward. And then particles are holes in the field. So that's important, and we'll get into that right after we talk about quantum field theory. So quantum field theory looks at fundamental particles as excitations in fields, spatial fields. Okay, so there's these fields of space, and the different excitations are different particles. But in quantum field theory, these fields of space all exist in the same spatial reality, so in the same universe. They exist in our in space together. They're all together, interacting. So in superspace theory, as we saw, these fields lie alongside each other, right? Moving from the energetic up to the entropic. So the fields lie alongside each other. And these fields would hold, not necessarily atoms, but if we go down here, quarks, superstrings, and get down to quantum foam, which I won't necessarily get into, but these fields would hold various types of particles. And so, instead of the excitations being in just fields that are all sort of together in a single space, the excitations are in fields which lie alongside each other, moving from the energetic deeper down or deeper in to the more entropic. So quantum particles are, well, let's say excitations for now, in fields that lie alongside each other in order from the energetic to the entropic. But actually, it's better to view all particles and bodies as holes in fields. So this is another of the tenets of one of the principles of this theory. Particles are holes in fields. A particle is a hole in a field whose horizon is located within a discrete, unique field within deeper space. So again, if we remember that block universe, where the fields lie alongside each other and then going up to our field of space, quantum particles would be within these deeper fields. So this deeper direction. So as we curve inward, gravity curving inward, and then curving into the fourth dimension or the fourth spatial direction, it curves down into deeper fields of space, and quantum particles would be held within these deeper fields. But this also tells us about the nature of gravity. But let's continue with the particles as holes in fields of space for now. The location of a hole's horizon determines the kind of particle it is. A particle has its particular nature because of the depth of the field where it is located. So this tells us why quantum particles, why nucleons, as they're called, why they have their particular nature is the depth of the field where they are located. So as we saw these fields lined up together, the different particles have different depths. So again, this is a very simple, and this is not really the best one, but down here, if you don't look at atoms and you just think of quarks, and then you could do like nucleons and then superstrings, if there's such a thing, they would be at different dimensional layers, moving from the entropic layer of our universe down toward the most energetic. And this continues down into the more energetic, and that direction goes infinitely. So there's no end to that direction. Okay, so when we look at quantum particles as having their nature determined by the depth of the field where they're located, we look at them as holes because by their nature, when you think of inward, the direction of in, as a direction that's infinite, so if you could think of this as a particle, and the direction inward is infinite. So that would make this a hole, like a black hole. So people have bandied around the idea that a quantum particle could be seen as a tiny black hole, and it precisely is. A hole is a better way of seeing particles because they have a center that goes inward to deeper and deeper dimensional fields. And that's the same for heavenly bodies, such as a planet or a sun. All bodies are holes in fields. Heavenly bodies in our universe are also essentially holes in the fields of space. What we observe as a planet or a star is the boundary or horizon of a hole. Now I'm going to use a graphic that's not my own real quickly under fair use, just to demonstrate that idea as clearly as I can. So, when we look at black holes, we acknowledge the idea of a hole in space, a hole that goes inward, what we would consider infinitely, right? So we allow that concept of a hole in space. Now I'm going to have to make my brush a little thicker. So a hole in space that goes inward, there's the event horizon, and it goes inward, I won't write the whole word, but infinitely, it goes inward infinitely. So we acknowledge this as a reality, but say we look at the sun over here, it's curving space inward, but we don't see it as a hole. Now there's something there, but it's still a hole. And see how the white dwarf is deeper and the neutron star is even deeper? Well, the hole keeps going, even if there's something there within the hole, an energetic reality there. The hole keeps going. These are still holes in space that have a center that continues going inward. It does not stop just because there's something there. It's still a hole in space, and that's what gravity is. So when we think of gravity, let's do a really crude little design. Actually, here, let's open something else. So when we think of gravity as curving space, I'll get one of my own graphics up here. So when we think of gravity as curving space here, right, so these lines represent curves, that curvature is a hole. It's not that an object curves space, is that an object is part of a hole in a field of space. An object is part of a hole in a field of space. So when we, in the classic visuals of an object in space, let's now we have to make it a little thicker for the better graphics. Okay, size. So when you see the pictures that show, you know, a planet, let's forget all the layers underneath, but you just see a planet and it'll show the curvature. You know, we've all seen these pictures, way better graphics. So the curvature of space, right, around the body, it's not that the body is curving space, it's that the curvature is the hole in space and the body is part of that whole. You could say it's something in the whole, but you could just look at it as part of that whole. So the whole, the reason space is curved is because a whole is there. And so the body is part of that whole. All bodies are wholes in space. What we observe as a planet or star is the boundary or horizon of a whole. The boundary or horizon of a whole. It's the same with quantum particles. So gravity, curving inward, is curving into this fourth dimension, this fourth degree of freedom, this fourth spatial direction, which is into the realms of the so-called very small. And so these are some of the main points of the principle of the equivalency of size and distance. And I can actually say it simply as not even the equivalency of size and distance. It can just be stated that size equals distance at fundamentally smaller levels of physics. So we're going to just put that here real quick. Size equals distance, and I can't spell. Size equals distance at fundamentally smaller levels of physics. Now, one last thing I'd like to touch on, and I won't go into it in depth, it's quite complicated, but one of the consequences is looking at time in a new way, which also affects how we view gravity. So one of the principles that come out of this is the unification of time and gravity, which sounds like nonsense until you understand it. So one thing we have to understand is the block universe is moving. And you can understand this in different ways. But what I'm just going to pull up this graphic. What I would like to just basically, let's actually look at these little fields up here. So we have energy here at the bottom, and then we have entropy at the top. Let's go ahead and open in GIMP, that way I can make little notes. So we have energy at the bottom here. I should have gone here. We have entropy at the top. And due to this energy, which moves in this direction, from energy to entropy, which is how energy works. Now we're talking about more fundamental things, which I will not get into here. But due to this energy, the block universe, here's a better arrow, the block universe is moving. So these fields of space, or the energy, all of it together, is moving from the energetic down here toward the entropic up here. So it's all moving, and it's moving in a direction of overall space that is the fourth dimension. So these layers, so here's our universe, and then there's these layers beneath. These layers represent, layers under our universe, so what we call the realm of the very, very small. In this direction, inward, is the fourth dimension, or a fourth spatial dimension. So if this is moving up, that would mean that the whole block, if this is moving up from the energetic to the entropic up here, if this is moving, that would mean there's a motion in this different, unrecognized fourth spatial dimensional direction. There's a movement. So it's not just that when we go into the realms of the very small, when we go in to these deeper fields of space, that it's not getting smaller, but that it's a fourth fundamental direction. It's that there's also a movement in this direction from what we would call small to large, but it's actually not small or large. It's in this fourth spatial direction. So all of our universe, let's, I don't know which is the best graphic here, but let's just say this, and we'll say all of our universe is moving in this fourth spatial direction. So here, let's look at the top here. So our universe, here's the Big Bang. So actually, it's the bottom one is the real one. So here's our universe, and here's quantum foam, and under the quantum foam would just be infinite energy, really. And these are fields of space, and they're moving in this direction. So that's hard to wrap your mind around, but when you do comprehend this, you can understand that this motion, this overall motion through the greater block universe, is what we think of as time. And I believe that is in here. Time is the directional motion of the block universe. Time is the directional motion of the block universe. So I don't want to go over this too much. I think it stands on its own once it's understood. And I'll go to one of the consequences of this principle is the unification of gravity and time, which is to say, gravity and time are aspects of a single phenomenon. The flow of time, which is the flow of the greater block universe, makes it the same as if a planet was moving up to meet objects within its gravitational curvature. And again, that's one that's a bit hard to get your mind around. We do have a graphic to help a little bit with that. I'm going to open with GIMP. And so the idea is, so this would be a sheet of space, and let's say that's our universe, and there would be other sheets underneath, but I didn't feel the need to draw them here. Now I'm going to do them really badly because I'm using a mouse. So this is the motion. This is the motion up. And so if this sheet of space is moving up in the direction of time, which, is actually just a spatial motion that we don't recognize because it's in this fourth dimensional direction. So if this space is moving up in the direction of so-called time, but just in the fourth dimensional direction, if this sheet of space is moving, then the curvature of space, if something was moving in linear space, and it met this lip, this horizon of a hole in linear space, then it would curve into it, right? But that's what we say with Einstein's theory of general relativity, that space is curved, and that's why objects curve down to planets, right? Let's put a planet here. But if you don't have the idea of gravity as a force, then let's say something curves into this planet and is stopped by the ground there. What would be sticking it here? What would stick it to this planet if it's just curvature and no force? Because once it hit this and was stopped, right? See, it's moving, it moves in and it's stopped, then what would be holding it here? Why would gravity hold us to the Earth? We would curve in because it's curved, but why would gravity hold us there? Well, if this is all moving up, then if something can't keep going inward, in other words, this is rising up over, this is complex, but the hole, this hole, let's forget the planet, it's a hole in space, is rising up, and if something is going this way, this rises up over the object moving through linear space. Okay, that's enough little lines there. So we'll bring up an undisturbed version just to try to go over this a little bit more before we call it a video. So now we can see more clearly, since it's not messed up. Again, this space is rising up, so the hole is also rising up. The hole is also rising up. And the curvature of the hole is rising up. So the object moving through linear space, when it reaches this point, it's not falling in, the hole is rising up over it and keeps rising. So this will end up going in just because the hole is rising up until, for instance, it's stopped by a planet. But because this is still rising, it will be held against the planet as this continues rising. So that explains why the curvature of the hole acts as a gravitational force without the need for an actual gravitational force. Now, before I sign off, there were a couple more things I wanted to just go back over using some of these other graphics. So when we talk about the idea of these fields in space that are actually lying alongside each other as dimensions lying alongside our own universe, this is, although the one original idea here is that when you go inward far enough, things are no longer getting smaller. At some point, once you get into the subatomic realms, things are no longer getting smaller. They're more distant in this fourth dimensional direction. That's the unique idea. But say, for instance, with the cyclic universe model, people have proposed the idea over here, we start with the Big Bang, that is two sheets of space, you could call them sheets or fields or branes, that bump into each other, which causes this energetic reality in our sheet of space because it got bumped into by another sheet of space, which I don't know why it would cause energy, but maybe this other sheet of space is energetic. It bumps into our sheet of space and creates that big bang of energy. And so you can look at this idea of two sheets parallel to each other. But the one thing we're not understanding is that the sheet parallel to our universe, deeper down, is in the direction of small. That what we think of as very small at fundamentally smaller levels is not small. It's a different sheet, different dimensional sheets, right, as I've already showed you. So this idea, and we also have it, this little graphic here, which someone created with branes colliding to create the Big Bang. Again, it's that idea. But what we're not understanding about this, and there's various models that look at sheets of space or dimensions lying alongside each other, okay? But what we're not understanding with these sheets, these fields, is that the direction they exist in is not some hypothetical direction where they're curled up very small or they're this or that. the direction they exist in is the direction of small. Fundamentally smaller levels are not small. They exist as a fourth spatial dimension lying alongside our own. So that's where I will sign off for today, but I do plan to make another longer video where I kind of surf the net, not just using my own graphics and the things I have already up, but where I surf the net and kind of go over some of these things with drawing up ideas and reading off of pages that will help support the idea. But that's some of the basics right there of Superspace Theory. And of course you can get the book. It's not at $5.25 now, it's $29.99, but this was just my original test price. But you can get the book, but that's not why I'm making the video. I'm making the video to share these ideas, and I appreciate your watching. Thank you very much. Oh, and you can go to the website in order to learn more. Thank you.